Hello, welcome back. Here we are going to revisit Chapter 11 and working with multiple comparisons and analysis of variance. And towards the very end, we will present we'll revisit linear regression again. Okay, but last time we talked about, the chi-square goodness of fit tests. And in here, we're just saying, if this wheel is perfectly balanced, these are the number of wins I would expect out of 3, and here's a probability of these wins out of 3. And we constructed this table where we had the expected outcome per cell and the observed outcome per cell. And just as a reminder in here, in StatCrunch, under the stat, there's actually a goodness of fit chi-square test. And so here, what you would put in one column, your observed counts for each cell, and then the expected, I guess that's expected probability within each cell, assuming the null hypothesis is true. So a lot of times, well, especially if you're using StatLab, they'll give you the data, but you may have to create a column of your observed counts, and then for each corresponding observed count, you have to get the corresponding probability to be in that cell. Okay, and there's also a button there. If each cell is equally likely, you can push it there and actually do each outcome. And so what this will do is actually give you your observed, your expected for each cell, and your chi-square and your chi-square statistic and your p-value. So it's pretty nifty here. But this is using the goodness of fit for goodness of fit test of chi-square. Also here, you don't have to put probability. You can put the actual expected outcomes. Okay, so you may see that in StatLab. They may not give you the probabilities, the expected probabilities, but they give you the expected counts. So you can actually put the counts here as well. And the goodness of fit test is going to know, because probabilities are between 0 and 1, and expected counts, they all have to be at least 5. Okay. But anyway, so in Chapter 11, we got into multiple comparisons. And so really what we're doing here is, in linear regression, we're looking for associations between numerical variables. And in chi-square test for independence, we're looking for associations between 2 categorical variables. And so really what we're doing here is, here we have our numeric variable, and then down here we have our categorical variable. So really what we're doing is we're saying, is time slept, right? Does it depend on which day it is, right? Is there association between time slept and day? So here we obviously are looking for a special type of association, which is between numeric and categorical now. Okay, so last time we did the multiple comparisons, and we just said, yep, well, when doing these, your type 1 error is going to go up. Okay, how so? Well, they call this the overall significance level, right? If we're doing 3 comparisons, this overall significance level, it's around 15%. And really that's just the probability of having at least one type of error, assuming these outcomes are independent. Okay, so this is kind of like worst case scenario. A lot of times these things are dependent. It's really not that large, but anyways. So, or it could be larger, but so we introduced Bonferroni correction. Okay, Bonferroni correction. And really, this correction, it works very well, but it only works very well for smaller data sets, okay, or for smaller comparisons. Even like 5 and 6, I mean, it could be really bad adjustment for this overall error rate. Okay, but in here we did this example here last time, but now let's get into analysis of variance. So what we saw with Bonferroni correction is that it may work for a small number of comparisons, but if we want to do more, what can we do? And what we learned with Bonferroni is that, well, if we have more comparisons, the type 1 error becomes very small, or the confidence level, the capture rate, becomes very, very large. And so what happens there is that your tests, they become very, very conservative, and they'll never reject a null. And so what we want there, we want to somehow come up with a better test such that we're taking to consider this overall significance level, but at the same time, we don't want our test to be too conservative. So analysis of variance is the cure for that, and that's what we're going to talk about right now. So here it says ANOVA tests whether a categorical variable is associated with the numerical variable. This is the same as testing whether the mean value of a numerical variable is different in different groups. Okay, so for example, this is I think the lifetime recorded. It's in in thousands, okay, for different types of tires, okay. So here we're saying, well, is this lifetime of a tire, this numerical variable, is it associated with the type of tire? And that's a categorical variable. So from this graph here, we can, just looking at these box plots here for each distribution of tire lives, and we kind of see differences here. We kind of see some pretty significant differences here between the lifetime of the tires, and Falcon is definitely the best out of all three. And so what that tells us is that there is a clear association between the life of the tire and the tire brand. Okay, if these things were not associated, okay, if they were not associated, all of these would look the same more or less. Okay, they would all more or less be centered around the same value. Okay, but they're not. So what ANOVA does is it'll formally test this, whether or not they're all the same or not. Okay, so so really this test for association is the same as testing whether the mean value of a numerical variable is different in different groups. And what we call this is a one-way analysis of variance. Now the reason they call it one-way is because we're only looking at one categorical variable, and what they leave it open for is we can actually add more categorical variables if interested, but for now we just do one way. So the null hypothesis for these tests, it says there's no association between numeric and categorical variable. Okay, an alternative says there is an association, and what that really means is that these population means differ by category. Right? So if you write them in terms of parameters, it's saying the null hypothesis is that the mean of group 1 is equal to the mean of group 2 is all the way equal to the mean of group K. Right? So all of the K groups all have the same mean. Okay, versus the alternative that at least one of the means is not equal to each other. Okay, so the nice thing about ANOVA is right away we can compare all the means, right? And if we fail to reject the null, then we conclude, hey, not enough evidence, therefore, we just assume that the means are all the same. Okay, and if we were to reject the null, then it means at least one of these is not equal. Okay, so it just could be 1 is different, or 2 is different, or you can have, who knows. Okay, but really, this is the first test we do. Now, if we do reject the null, we go in further and figure some more stuff out. Okay, but ANOVA, they call it analysis of variance, but yet the null hypothesis is about the means. Right? So these next two slides are very important into understanding what the ANOVA test is doing. Okay, so the reason they call it ANOVA, analysis of variance, right? So what they're saying is that it compares the amount of variation that exists between groups with the variation within each group. And so in this example, I go back to the sleep study, and so here alcohol use is categorical and average sleep is numeric. Then the variation is large within groups and the variation is small between groups. Okay, so what we mean by within groups, we're saying here, okay, the variation, if you look at abstain, let's look at the variation of sleep time. Let's look within heavy. Let's look at the variation within heavy. Let's look at light. Let's look at the variation within light. Let's look at moderate. Let's look at the variation of sleep within moderate. So what we're saying is that within each group, this variation is relatively large. Okay, it's relatively large. Okay, and then this is saying the variation is small between groups. So really what we mean is, as you compare this, now we're looking not individually, but we're looking at all together, is let's look at the means of each group. Right, the means of each group. How much do these means vary? Right, not as much, right? Because within group we're going from like 6 to 11, 6 to 9, 6 to 10, 6 to 11, right? So but here, if you look at these green values, right, the variation between groups, right, with the mean goes here to 7.9, and then it goes to 7.8, then it goes to 8.1, then it goes to about 8. You see those, there's not a lot of variation. So we said the variation is small. Okay, so in this case, what our test would do if the variation is large within groups and the variation is small between groups, we would fail to reject the null. Okay, if our data looked like this, we would fail to reject the null and conclude that all the means are the same. Okay, but they would compare this variation between and the variation within. Okay, so it's a very important concept in understanding what this ANOVA output is giving you. Okay, so now if we were to reverse it, let's look at the variation is small within groups and the variation is large between groups. So if you look at within groups here, we're varying, all these box plots, there's not that much variation in them, right? They're kind of all crunched, between like 4,000 miles, right? Kind of 4,000, 4,000, 4,000. So that's within groups, right? So within groups, if we just look at the boxes here, 32 to 36, 31 to 33, and we got down to 32 to 36-ish again, and then here this is like 36. So the variation within each group is not very large. Okay, it's not very large. Okay, and then we say the variation is large between groups. So now if we think of these as the means, I mean these are somewhat close to the means. I mean they're the medians, but we have the value here, one mean here, one mean there, one mean there. So as we're traveling between groups, we're tracking how much variation that we have here. Okay, so here if you look at the means, they go from 32, right, all the way to 38, right, about 38. So in comparison to within groups, the variation is large between groups, right? These averages vary a lot, right? And obviously by the picture here, we could see, I mean, there are clear differences in the mean lifetimes here. Okay, there are clear differences for the mean lifetime. So in a case like this, we're obviously going to reject the null hypothesis. Okay, so as you can see here, how we're comparing the variation within and between to make decisions. So in the previous slide, we're saying variation is large within, but small between, right? So we're looking at we're looking at the means, right? And these are the means. No big difference. We're probably not going to reject the null hypothesis. Here, the variation is small within groups, but large between, right? So it's small within, but then large between. Okay, then we're more likely going to reject the null hypothesis, right? So that's what hypothesis testing does for the ANOVA. It's comparing the variation between and the variation within. That's why it's called the analysis of variance, right? Okay. So that's what we use here. So as far as the numerical quantity, what's our F-test statistic? Well, it's saying F is equal to the variation between groups over the variation within groups, right? So what it's saying here is that if the variation between groups is big relative to variation within groups, then F will tend to be a large number. Okay, so that's what this is here, right? The variation between is large relative to within. Okay, and what this is saying, if the variation between groups is small relative to the variation within groups, then F will tend to be a small number. Okay, and that's what's happening here. Okay, the variation between, right, these green are very small, and the variation within is a little larger. Okay, and what we're going to do is, as you suspected from this graph here, okay, is that we will reject the null hypothesis for large values of the F statistic. So if we were to want to test the hypothesis here, we would say, okay, here we wish to test the amount of weekend sleep, which is a numeric variable, is associated with reported alcohol use, which is categorical, and that is, under the null hypothesis, the mean weekend sleep for the abstain group is equal to the mean amount of weekend sleep for the light group, is equal to the mean amount of sleep for the moderate group, which is equal to the mean amount of sleep for the heavy group. Okay, so I mean, in terms of alcohol, these abstain, these are light drinkers, these are moderate, and these are heavy. Okay, and where the alternative is just at least one mean is different. Okay, so I don't know where they're different, right? We're just saying at least one. So if I were to run this example in StatCrunch, okay, so in StatCrunch there is an ANOVA calculator, okay, we would get the summary statistics within each group, okay, and we're going to use these later, and then we would get our ANOVA table. So here, this is our F statistic, right? So, and this is our p-value. But right now we'll just focus on the F statistic and really interpret it and see what does that mean. Okay, but before I do that, let me just show you how I did this in StatCrunch. Okay, so in StatCrunch, I went to, so this is the sleep study data. So I did stats, and then I did ANOVA, and then I did one weight. And then here I'm saying my responses by numeric variable is weekend sleep, and my factors, my categorical variable, is alcohol use. Okay, and so if you hit compute, there is your table that we asked for here. Okay, so exact same thing here. All right, so remember this F statistic. Okay, this F statistic tells us, okay, so it gives us the variation between groups over the variation within groups. So this value is 2.14. So what that tells us, it tells us that the variability between groups was 2.14 times greater than the variability within groups. Okay, so remember, we're going to reject if this number is large. How large does it need to be? Well, of course, it depends on the p-value here. But of course here, that's how we interpret this F statistic. Okay, so all these statistics, test statistics, they all have an interpretation. And this is how it works for the F. So just in terms of the table, okay, if I show you the table here, you see a lot of new notation: source, DF, error, SS, MS. Okay, so we're going to explain what these mean in a second. Okay, so when you see total sum of squares, on the very bottom we see total. Well, there's total sum of square, and what this measures is the total amount of variation. So we're talking about variation, which is, you know, the sum of square differences here, okay? And this total sum of square, it can be broken down into two pieces: explained variation and unexplained variation. Okay, so explained variation is always in terms of our categorical variable. Okay, and what the explained variation says, it says, look, given the categorical variable, right, how much does it tell us about the numerical variable? Meaning, oh yeah, students who drink heavily, they're definitely going to sleep more during the weekend. It's obvious from this graph. All right, so that's what we mean explained variation. Okay, if this categorical variable is effective at all. Okay, so this explain or treatment variation, SS, is equal to the variation between groups. Okay, the variation between groups. So that's just telling you how much of the variation in the sleep amount or the numeric variable is explained by the categorical variable. Okay, not exactly, but that's kind of what it is. Okay, if you remember R squared, the coefficient determination from linear regression, right? And what that did, it told us how much what percent of variation in our response variable was explained by the predictor variable, right? And this is doing more or less the same thing, but our predictor variable is no longer numeric, right? It's categorical. Okay. Unexplained or error residual variation, SS, that's the variation within groups. Okay, the variation within groups. And then we want to compare these two variations, but they're not on the same scale. Okay, so we need to standardize them. So what we do is we just take the mean sum of squares, right? So what we do is we divide our sum of squares here, our sum of squares here, by their appropriate degrees of freedom. All right, so that's what we say here. So these variation between groups right away, it's not, we can't compare them right away. They're like apples to oranges because they're on different scales. So what we do is we take the average square distance and then we compare those two together, right? And so that's what we get here. Okay. So, I mean, here, these are just kind of getting a little deeper into what this table is giving us here. Okay. And if we go into the table here, right, so here it's saying source alcohol use. So this is the variation between groups, okay, between the different groups of alcohol use. And this error, this is the sum of squares, or the amount of variation in within groups, okay, within groups, okay. So what SS stands for, it just means sum of squares. So pretty much how they calculate these numbers is here they find the average sleeping in each group, okay, the average amount of sleep within each group. So for light, moderate, heavy, and then what they do is they take the difference between the mean in the group and the overall mean if there were no group, and then they square it. Okay, so that's what they're doing there to get these here. These are a little different, but I won't give the equations for these because it's a little confusing as far as summation, but you just have to be able to interpret it. Okay, this is just the amount of variation between groups. This is the amount of variation within groups. Okay, and then here what they did is they did this number divided by degrees of freedom. So the degrees of freedom for treatment here is just your number of treatments minus 1. So here's 4 minus 1. That's how we get that. And then for your degrees of freedom here for within is just your total sample size minus your number of treatments. Okay, so they just did this number divided by degrees of freedom to get this mean square error here. This mean sum of squares. Okay, so and then they just put this number over this number to get that statistic there. Okay, to show you that the variation. Right, so right away we can't compare these because they're like apples to oranges. So we get them on the same scale by dividing by their respective degrees of freedom, and now we can compare them. Okay, so when we divide this, the mean sum of squares for alcohol use by the mean sum of squares for the error, or between and within, we get this F statistic here. Okay. One thing to note about this total sum of square is that it's broken down into explained variation and unexplained variation. So if for some reason they gave us total sum of squares and treatment and between sum of squares, well, you could just do total minus this to get this number here, okay, or anything. If you're given two of these and missing one, you can always find what it is. But this represents the total sum of squares here. This is the total sum of squares. And we're saying that this total sum of squares can be broken down into the explained variation plus the unexplained variation. So that's what the table's giving us there. Okay, and like I said right away, we can't compare these right away because it's like comparing apples to oranges. So once we divide by the respective degrees of freedom, now we can compare them. Okay, and this is what we get. This is saying that the explained variation by the treatment variable is 2 times larger than the unexplained variation within groups. Okay. So usually in the tables, as far as looking at this table here, how does StatCrunch get these numbers here? Okay, how do they get all these numbers here? So I will show you how they get most of the numbers, with the exception to these, because there's just, you know, as long as you get the idea, right? This is the variation between, this is the variation within. That's the important, how to interpret the number. But to calculate it, the summation notation is not very nice, and I'm just going to save you from that. Okay, but here in this example, what we have is just saying, well, degrees of freedom of treatment is just your number of treatments minus 1. Degrees of freedom of the error, it's your sample size, your total sample size minus your number of treatments, and your total degrees of freedom is your sample size minus 1. Right, so this represent here, I mean, this looks kind of familiar, right? So this is just your total sum of squares. So what they do is they just take one overall average, right, and then just take the square differences, right, the square differences, and then they sum them. So that's why they're called sum of squares, sum of square, right? Because what they're doing is they're looking at the distance, and they square it, and then they're summing over all the observations. So there are similar summation notations that belong here, but I'm just going to save you from it, and just to make sure, you know, looking at the graph, you can visualize what they're going to be. Okay, And then to get this mean of sum of squares, we just do whatever number we get here divided by our degrees of freedom. And then to get the mean sum of squares for error, well, we just take whatever number we get here and divide by our degrees of freedom, okay, to get our F statistic. Okay, but next time we'll get into a little example, but we'll take a break for now.